Hello, everyone. This is Team 1032, consisting of me, Lucas Hines, Isaac Taylor, and Connor Tong. Coached by Andrea Hines, we are from MMC&M. We worked on Problem A, introducing stress. Problem A tells you to develop a mathematical model of the stress and capabilities of a group of people. We're assuming that there's an existing group of people in place at the destination who are already under a great deal of pressure to complete their assigned tasks. The model should include the addition of a second group of capable people who arrive after undergoing the stress of a space launch and do not have prior exposure to the new environment. Given the expected stress levels over time, what is the impact on the whole group? Assumptions. We assumed, of course, that effort, stress, and fatigue are all quantifiable, that the fatigue level of each individual is related to an arbitrary variable effect, the stress level of each individual is related to the workload of the crew, that the efficiency of the work done is dependent on effort, fatigue, and stress, and the work-effort efficiency relationship of each individual is the same. The way we formatted the problem with each person having two different states, awake and asleep. Each person contributes work effort as a function of the amount of time they sleep. While a person is asleep, they have an effort coefficient of 0, and while they're awake, they have a positive effort coefficient less than or equal to 1. A person's change in fatigue is dependent on the work effort. A person's rate of increase of stress is related to the workload level. And we're formatting it where T represents time in days. Here are our equations. We have the rate of increase of fatigue represented by T prime of T is related to effort by this equation, by the first equation. The rate of increase of stress represented by S prime of T is related to workload, and work efficiency is related to stress, effort, and fatigue. And finally, the rate at which work is done is directly related to work efficiency, the initial conditions down here. And here's how we implemented everything in Wolfram Mathematica. I used the ND-solve function, which models the system using Filipov continuation. I then plotted the graphs of the functions of interest. And you can see my code there.
This is experiment 1. We used a binary sleep function where we modeled a simple work, not work, sleep, not sleep function as shown below. This is a piecewise function showing that at certain points of the day, there's either work or no work being done. C is represented by the proportion of the day that work is being done. For instance, if C was 0.5, then they would not work for the first half of the day and then work for the second half of the day. It's experiment 1.1, where we set C equals 0.4, which means that the crew is resting for 0.4 of the day. As we can see in this example, while they start out with keeping the work somewhat under control, once exhaustion sets in, they manage to lose control of the workload. At C equals 0.45, the crew is working for most of the day. While they start out with keeping the work under control, still, once the exhaustion sets in, everything falls apart. At C equals 0.5, the crew gets enough rest, sleep, and is able to keep the work under control by limiting stress. At C equals 0.55, the crew gets enough rest and is able to keep everything under control. This seems to be the optimal constant C. And at C equals 0.6, the crew rests for too long and is not able to keep the workload under control. So we
So-
model a sim.
Our second experiment, we modeled a simple function where the crew works at a constant effort level throughout the day. If c equals 1, we see that we have a bit of a setback because of the negative workload and the fact that exhaustion can only go up so fast. So by the time fatigue is basically 1, stress is already at around 0. So the crew ends up maintaining control of the situation, even though they are completely exhausted. At c equals 0.8, we see pretty much the same situation, where fatigue is just going all the way up to 1. And at c equals 0.6, the crew does not work enough to keep up with the workload. And lastly, experiment 3, we used the sine function to model effort. It seems here the crew does not get enough rest, but still somehow manages to keep the workload under control. Limitations of this model are that while mostly accurate, first of all, we can't fully model human psychology in this model. There would be, in reality, a lot more factors, especially with a new second group of people coming in. And also, there are often cases where we just got completely illogical results, like, for an example, completely chaotic graphs in cases where things should have logically settled down.
Thank you for watching. We hope you have enjoyed our presentation on problem A. Yeah, that's all. Thank you.